Now, let's enter into a new topic called visualizing 3D in 2D. What do you mean by 3D or 2D? When I call it with 3D, I refer to this as three-dimensional. When I write 2D, I refer to this as two-dimensional. But what do you mean by three-dimensional or two-dimensional? Is one of the biggest questions when we discuss about the topic visualizing 3D in 2D. We all have seen a 3D movie in the theaters. The movie which you generally see on a 70mm screen in general in most of the theaters is a 2D picture. But some of the movies which are shown are given with the name 3D. So what makes the difference between a 3D movie or a 2D movie is how we understand this concept. The 3D is that we have, in this case of two-dimensional, I have two axes, x and y. For two-dimensional, I have two axes, x and y. So it is always referred with x and y axis, whereas the three-dimensional is referred with three axes, x, y, and z. It's something like this. You have x, y, and z. So when it comes to this concept of understanding three-dimensional, that means anything which occupies space in general sense is called a three-dimensional object. So when I take a picture, say for example, I take a box. I visualize this as a box, but this is not exactly a box. This is a box drawn on the board, which is visualized as a three-dimensional object. So when I take this, I understand this to be a box because I can feel it in general. I can feel this in air and I can hold it, and this has been occupying some space. Therefore, in this room, I call this as a three-dimensional object. But when I draw the same picture on the board, say I just draw this is a two-dimensional picture of this three-dimensional box. So this is a 3D object, and I visualize this 3D object as a 2D object on the board, is how I understand between two-dimensional and three-dimensional. Why don't I call this as three-dimensional object? I only visualize this to be a three-dimensional object. Why? Why is it not 3D? Is the biggest question out here. Why not 3D? Because I cannot move this box into the air and feel it. This does not occupy space in air, but this occupies space on the board. So this is a two-dimensional picture of a three-dimensional object, a box, which I have taken in this case. So therefore, this is how I understand between a two-dimensional picture, which is visualized as a three-dimensional object, but actually it is not a three-dimensional object. It is only visualization. The actual three-dimensional object of this two-dimensional picture drawn on the board is this, occupying space in the air. Now, coming to this concept, so in general, mathematically, we define three-dimensional object as that object which occupies space in air, that is, which is along all the three axes, x, y, and z axis. And two-dimensional object is along only x and y axis. So if you just take one more example, let me take this book or a diary which I have. Now, if I take each of the page, rectangular page, and then I join each of the page, then I construct with each of the page a cuboid or a book. So a cuboid is obtained by putting each of the sheet on one over the other on the top, so that I get a three-dimensional cuboid from each of the rectangular piece of paper or a rectangular sheet. So this is how I visualize, where one sheet over the other would construct a cuboid. So construction of a cuboid is that when you take a two-dimensional plane surface and add it infinite number of times until the height h, then I get the total cuboid, a three-dimensional object. So that is one more way of understanding the construction of three dimension, or the difference between a 3D and a 2D object. So that is how a 3D and a 2D object concept is understood in this concept. Now, when it comes to 3D object properties, we have already discussed about two-dimensional objects like quadrilateral, triangle, a rhombus, a parallelogram, a trapezium, and various other properties in plane figures of two-dimensional objects. Similarly, we have some properties for three-dimensional objects like a cube, a cuboid, a prism, or many other objects which are called geometrical solids. The difference between two-dimensional and three-dimensional objects are that three-dimensional objects are solids. So, as solids which occupy space in air. So, in this case, when we understand the three-dimensional objects, there are three important key factors we understand indirectly for three-dimensional objects. One is the points, or we call them as vertices, and the edges and the faces. So, the vertices, edges, and faces make a three-dimensional object or a three-dimensional geometrical solid. So, these three make a three-dimensional geometrical solid. So to construct a geometrical solid which is three-dimensional, I need the vertices, I need the edges, and I need the faces. Say for example, how this can be constructed. Let's construct a cube using these concepts. So when I take this, let's construct a cube which is a three-dimensional object. We all know that this is a sort of a cube where all sides are squares. Each of the face is a square. So before we construct, let's take into consideration the vertices or points. Now where I have this, I first take the points which are edges, which are the vertices. So these are the points, are the endpoints which are taken in case of a cube. So this is one of the endpoint, that is one of the vertex, and here is one of the endpoint, 1, 3, and 4. 1, 2, 3, 4 is one which I have taken as 1, 2, 3, 4. Then I have taken the side 2, 1, 2. Then I have taken the other 2, 1, 2, and then finally 1, 2. So totally I have 4 edges on the top, 4 endpoints on the top, and 4 endpoints on the bottom. So totally a cube has 8 endpoints, counting from 1, 2, 3, 4, and then at the back 5, 6, 7, and 8. So these are the endpoints which are called vertices for a three-dimensional geometrical solid. So when I take the example of a three-dimensional geometrical solid which is a cube, I have totally 8 points, 1, 2, 3, 4, 5, 6, 7, 8, which are taken, which are the vertices of the three-dimensional object. And once we know the endpoints, we can construct the edges. Now what are the edges for a cube or any other three-dimensional geometrical solid? The edges are the lines connected between the endpoints. Suppose I take, say, this face. In this face, this line connecting the two endpoints is one of the edge of a cube. Now this endpoint and this endpoint, when connected through a line, is called another edge. Edge number 3, edge number 4. So how many edges are there for this cube? Edge 1, edge 2, edge 3, and edge 4, and then turn back 5, 6, 7, 8 is one more, and then 9, 10. This is already included, and then 11 and 12. So there are totally 12 edges which are there in case of a cube. So each of the edge is obtained by connecting the pair of endpoints, adjacent endpoints, which you are connecting. So this is how the edges are formed, where the face turns. Edge is the junction where the face of the cube turns. So this is turning at an angle because you have an edge here. So edge is indirectly referred as the junction where the face of the three-dimensional geometrical solid changes its direction. So when I take the edges, I have, these are the edges, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So totally I have 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. If I count them, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So here are 12 edges, and here are the points, which are 1, 2, 3, 4, 5, 6, 7, 8. So here there are 8 points, 12 edges, and let's come to the faces. Now, how are the faces formed? The faces are formed by the regions, or the surface between the edges is nothing but the face. So if I take the edges of this, then the surface between the 4 edges is nothing but one face of the cube. Then this face between the edges is another face of the cube. And if I take these 4 edges, then the 4 edges have some region in between, which is the surface, which is called the face of the cube. So totally, if I count the number of faces, I find that there are totally 1, 2, 3, 4, and then on the top, which is 5, and the bottom, which is 6. So totally 4 lateral faces, and 1 on the top and 1 in the bottom, which make totally 4 plus 2. This is 6 faces. So this is how a cube is formed with different faces. So this is how a cube is formed between the edges. So if I take the 4 edges, then the region between the 4 edges is called face 1. And this is called face 2. And face 3, 4, 5, 6. The other 3 faces are not visible because the direction is in this. But as I take the box, I can clearly see all the 6 faces. 1, 2, 3, 4, 5, and 6. And the 6 faces which I find in this. So in case of a cube, I identify that there are 8 vertices, 12 edges, and 6 faces is how I understand the properties of 3-dimensional objects. 3-dimensional objects are always constructed from points and then to edges and then to the faces. Then this forms a solid 3-dimensional geometrical object. So this is how a 3-dimensional geometrical solid is constructed from step 1 to step 2, finally to step 3, is how I understand. And also, I can also identify the number of vertices, number of edges, and number of faces for each of the objects by counting them through the visualization of a 3-dimensional object. So let's come to the next topic, which is polyhedra. So this makes us understand exactly on the specific 3-dimensional solids, geometrical solids, which we are considering in this case to identify the vertices, edges, or faces of the 3D objects. So when it comes to polyhedra, the definition says that 3D objects which have flat surfaces. So any object which has flat surface is a polyhedra. This being an example where if I take every of the face, it is flat, but it is not curved. So in each of the face which is considered must be flat for the entire object to be called as polyhedra. This is a polyhedra, an example of polyhedra out here. So for example, I take cube, cuboid, and prism, etc. They're all polyhedra because each of their faces are flat in surface. They are flat surface. Therefore, these are the examples of this. For example, I take this is a cube. So this is a polyhedra because each of its face is flat. Each face is flat. For example, I take another so this is a prism. So this also, each face is flat. Therefore, this also is a polyhedra. Each face is flat. Therefore, even this is a polyhedra. Let me take now this is a cylinder. We all know that this is a cylinder, but this is not a polyhedra because this face is not flat. this face is curved. We all know that a cylinder has lateral surface which is curved. So this lateral surface being curved, this cannot be an example of a polyhedra. A polyhedra, but not a polyhedra. Similarly, I can take a cone. Is not a polyhedra because this is curved surface. This is a curved surface. When I take this surface, it is curved. This surface is also curved, but this surface everywhere is flat, and this also is very flat. Is how I understand the difference between the polyhedra and the non-polyhedra, with this being the example and the definition cases. Polyhedra and non-polyhedra, flat surfaces and non-flat surfaces respectively. So now that we have seen the definition of polyhedra, where each of the faces is flat or each of the surfaces is flat, then coming to the different types of polyhedra, there are two types of polyhedra identified in the branch of mathematics. So when I take the polyhedra, they are differentiated between the regular polyhedra and the other is non-regular polyhedra. So this is how I differentiate between regular and non-regular polyhedra. So what is a regular polyhedra and what is a non-regular polyhedra is the question out here. So before I explain the definition, let me draw one of the diagram, a three-dimensional solid figure, geometrical solid, and then try to understand the difference between regular and non-regular polyhedra through that example solid. So when I just draw here, say for example, I draw the cube, and here I draw the cuboid. So I call a cube as a regular polyhedra, but a cuboid as a non-regular polyhedra. Why? The reason here is that I define a regular polyhedra where each of the face must be equal. Say for example, I take back the cube. I find that the area of the face at this junction is equal to the area of any other face. So areas are equal. Not only that, the lengths of the edges are also equal wherever we take. So when I take the area of the surface is equal in all 6 sides, and the length of the edges, as you take from any of the measurement from one endpoint to other endpoint and to any other endpoint to any other adjacent endpoint in any of the other face, I find that the lengths are same in case of this. So I call this as a cube because each of the lengths are same and each of these areas, the surface areas, are congruent. I can say each of the face is congruent. Therefore, in case of regular polyhedra, the rule is that each face must be congruent to the other faces. So you take any two pairs of faces of a regular polyhedra, they must be congruent, which is in the case of a cube because area of each of the square is same. So that is the first condition for regular polyhedra. Then secondly, because they are congruent, then obviously the length of edges must be same. So obviously the length of edges would obviously be same because the whole of the face is congruent. So the length of edges must be same. You take from any face, when you measure the lengths of edges, they must give the same value. Is how I understand a regular polyhedra, a cube being one of the example, a cube out here. And thirdly, the third property says that vertices must be formed by equal number of edges. So the third point, let me discuss with a three-dimensional real object, where what do you mean by vertices must be formed by equal number of edges? So when I take, say, one of the endpoint, which is the vertex A, say for example this is vertex A. Now this vertex is formed by the intersection of all these three edges. So edge 1, edge 2 and edge 3, all three merge together. As you can see here, this vertex is formed by edge 1, edge 2 and edge 3, all three meeting at one point. So you take any vertex, you must have exactly the three edges which are intersecting to form one point of intersection, which is the vertex. So every endpoint, as you can see in case of a cube, is formed by three edges which are intersecting at that point. So that is also one of the property which is considered in regular polyhedra, where vertices must be formed by equal number of edges, as you can see here. So here all the vertices are formed by equal number of edges. So in case of all these three cases, when satisfied, I can call this as a regular polyhedra. Even if one of the condition fails in these three, then I cannot call the three-dimensional geometrical solid as a polyhedra. A cube is a perfect polyhedra out here. A perfect regular polyhedra out here, because cube satisfies property 1, 2 and 3. Now coming to the non-regular polyhedra, as I've taken an example of a cuboid. Now in case of a cuboid, what happens that this is not regular? What property is not satisfied in all of the three cases? Now when I go with the third property, I can identify that in a cuboid, every vertex is formed by the same number of edges. Suppose I take this vertex, edge 1, edge 2 and edge 3. So there are equal number of edges which form the vertices. So cuboid satisfies the property number 3. Well and good. But when I come to the property number 2, length of edges must be same. I don't think this property is satisfied by a cuboid, whereas it is satisfied by a cube. So the length of edges, which is length here, breadth and height, are of not same dimension. Therefore the length of edge connecting these 2 points AB and the length of edge connecting the points B and C may not be equal, because the edge connecting B and C is smaller, as you can see here, and this is bigger. Therefore cuboid fails in condition number 3 in case of non-regular polyhedra. This fails in property number 2, and also it fails with property number 1, because each face must be congruent to other faces. That means they must be equal in area exactly. So I can see that the upper and the lower areas are same, but when you take the adjacent areas, it fails in all faces being equal and congruent to each other. Therefore this also fails. So this is how we justify between a regular and a non-regular polyhedra. So this being a polyhedra and this being a regular polyhedra, this being a non-regular polyhedra, is how I differentiate between regular and non-regular polyhedra. So let's take another example of regular and non-regular polyhedra other than cube and cuboid. As I can see here, this is called a triangular pyramid. The pyramids, as we see in Egypt, is similarly a triangular pyramid of this shape, where each of the face is a triangle. So a triangular pyramid, even the base is a triangle here. This is a square pyramid, because though the lateral faces are all triangles, the base is a square. So this is called a square pyramid. So let's see which of them is regular and non-regular. Clearly I can see that each of the faces here, there are totally 1, 2, 3, 4 faces, 3 laterally and 1 being the base. Now all of them are triangles congruent to each other, and length of each edge is same, and also each vertex is formed by joining 3 edges. So this vertex is formed by forming the intersection of edge 1, edge 2 and edge 3, and every vertex when compared forms equal number of edges intersecting to form the vertex. Therefore, since this satisfies all the 3 properties of regular polyhedra, a triangular pyramid, which is also called tetrahedron, is a regular polyhedra. But this is not a regular polyhedra, because each of the faces is not a triangle. As you take the base, it's a square. Therefore all faces are not congruent to each other. which is the case which fails. Even the length of edges may not be same here. So therefore, this cannot be a regular polyhedra, but this is a non-regular polyhedra. An example of a non-regular polyhedra is square pyramid. An example of a regular polyhedra is triangular pyramid or a tetrahedron, and a cube. Cuboid and square pyramid for non-regular polyhedra is how I differentiate and understand the differences between regular and non-regular polyhedra. So there are two types of polyhedra. One is regular and the other is non-regular. So let's see the definition of a prism, which is a very important definition in case of a three-dimensional geometrical solid. One of the three-dimensional geometrical solid called a prism has its own specific definition. So the definition says that a solid object, any object which occupies space in air with two parallel and congruent polygonal faces, the first condition is that the object must have two parallel and congruent faces. This is the first condition for the prism, two parallel and congruent faces. Then secondly, the faces must be polygonal. So the faces can be any polygon or n-gon, and n-sided closed figures can be their faces, but they must be parallel and congruent, exactly equal in area. So the condition is they must be parallel, they must be congruent, they must be polygonal. So these faces must be polygonal. And when I talk of the lateral faces, now when I talk of lateral faces for this of a cuboid, it is taken along this, and these are the faces which are congruent faces or polygonal faces. So I take this and this to be the two parallel and congruent polygonal faces, and the other lateral faces are these. So let's see what happens to this thing. The lateral faces must be rectangles or parallelograms, is how I understand the concept. So when I take these three cases, then I can call the given three-dimensional object as a prism. So let's take an object and identify for that to be a prism. Let's identify these three properties in case of one of the object. So let's take an example of a prism which satisfies each of the cases, the three cases as considered. So let me draw one of the example which we all know is, say for example, we all know that this is a cuboid. So I have taken a cuboid which is just put in horizontally on a plane surface. Now this cuboid, let's see if this can be called a prism. So the first condition for this three-dimensional solid object to satisfy for being called a prism is that the two faces must be parallel and congruent. So other than the lateral faces, if I take these four as the lateral faces, 1, 2, 3 and 4 as the lateral faces, then the top and the bottom are called non-lateral faces, which must be parallel and congruent. So the non-lateral faces, the first and the second, the top and the bottom, must be parallel, as we can clearly see that they are exactly parallel to each other. The surfaces are parallel, and not only that, they are congruent because the area of this face on the bottom, which is a square or a rectangle, is exactly the same as area of this face, which is also a square in this case. So we can see that the two faces, the two non-lateral faces are congruent and are parallel, satisfying the first condition. So this object satisfies the condition number 1. Now the second case out here is that those two faces, the non-lateral faces which are considered, must be polygonal. So the non-lateral faces must be polygonal. Now we know that a polygon is an n-sided figure, therefore clearly a four-sided figure is a polygon, a foregone. So this being a polygon also is satisfied that the faces are polygonal. So the non-lateral faces are polygonal, parallel and congruent, satisfying the first two cases of being called a prism. Now the third condition is coming to the lateral faces. Now switching on from non-lateral faces, I switch to the lateral faces, where the lateral faces must be either rectangles or parallelograms. This is important because this is where the decision factor comes in case of a prism. So when I take the lateral faces, they can only be either a rectangle, opposite sides are parallel and equal with each angle 90, or it can be. So my lateral faces can be either a rectangle or it can be a parallelogram where opposite sides are parallel and equal, but each angle is not 90. So my each of the lateral face 1, lateral face 2, lateral face 3 and lateral face 4 should be a rectangle or a parallelogram. Now because each lateral face in case of this object is a rectangle, the non-lateral faces are parallel and congruent, and each of the non-lateral face is polygonal, I can call this to be a prism because it satisfies all the three properties as defined for a prism. I can call this cuboid as a prism, or this three-dimensional cuboid can be called a prism because it satisfies all the three properties. This is how I justify a prism in its three-dimensional shape. Similarly, there's another prism which we can also take into consideration, where I have, say for example, a hexagon, a six-sided polygonal face which is non-lateral and connected with so each of it is connected again here with so you get a similar shot of a figure. Now let's take the other example of a prism where one of its non-lateral faces, the pair of non-lateral faces are pentagons, the five-sided polygon or a figon. So when I take the pentagons, the regular pentagons on the non-lateral faces, clearly if these two are parallel and congruent and they are polygonal being a figon, then the first two conditions are satisfied for this. And the lateral faces being rectangles, as you can see in each of the cases, therefore this also can be called a prism, where this is called a rectangular prism and this is called a pentagonal prism. The name given based on its non-lateral face shape. So this is how I understand between a prism and the one which is not a prism. So if even one of the condition of all these three is not satisfied by the three-dimensional geometrical solid, I cannot call that solid as a prism, strictly with its own definition in this case. So let's see the other solid which is more famous in three-dimensional object in the concept of mathematics, called the pyramid. So pyramid is exactly the Egyptian pyramids which we see in the historical facts. So when it comes to a solid object whose base is a polygon and its lateral faces are triangular, is called a pyramid. So here the condition is that the base must be a polygon and lateral faces must be triangular. As simple as the definition. So there are two cases which define the pyramid. One is the base must be a polygon or an n-sided closed figure and its lateral faces must be triangular. So let's draw one of the example pyramid through which we understand the concept. So the Egyptian pyramid, which is exactly in this form, is one of the example of a pyramid. Now this is called a pyramid because its base, this is the base and this is a four-sided closed figure and this is a quadrilateral, a four-sided, or a four-gon, which is a polygon with four-sided, or a quadrilateral, and then its lateral faces are triangular. So you take each of the lateral faces. There are four lateral faces here which are triangular. Therefore, these two conditions satisfy for polygon and triangular. Therefore, this object is called a base pyramid. If I take this closed figure as a square, if I imagine this with all four sides equal, then this is called a square pyramid. If the base is a rectangle, then the pyramid is called a rectangular pyramid. If the base is a parallelogram, then the pyramid is called parallelogram pyramid. So the base will decide the name of the pyramid based on what kind of shape is here. So in case of this, if I take it as square, I get a square pyramid. So this can be called a square pyramid with base assumed as square. A square is how I understand a pyramid and its varied definition. There are many such pyramids I can take. If I take a pentagonal pyramid, then I have, this is my pentagonal pyramid where the base is a pentagon and each of the face is a triangle, is a pentagonal pyramid. This can be called a pentagonal pyramid because the base is a pyramid and each of the lateral face is triangular. Now, when I connect the pyramid with prism, then what is the very important property which I identify? What is the difference between a prism and a pyramid? So when I see here, it's very important note that when I take a prism, this reduces to a pyramid. A prism reduces to a pyramid if one of its prism's lateral face, if one of its non-lateral face, if one of its non-lateral face of the prism converges to a point. So what happens when one of the lateral face converges to a point? Then each of the face also converge to one point. Therefore, this becomes a triangular face and one of the lateral face vanishes to become a vertex. Therefore, we get a pyramid out of a prism. So if I take, say for example, this of a cuboid, which is a prism, a rectangular prism, if one of the face has all its 4 points coming together, then its adjacent points also come closer and closer and closer and merge with one unique point, so that one of the face will be a square or a rectangle and each of the lateral faces would exist, but they converge to become a triangle. So every rectangle converges to become a triangle. So each of the rectangle converges with this point and this point merging to become a triangular face. So therefore, each of the face becomes a triangle. Therefore, a square pyramid is formed when a square prism, say for example, this is a square prism where these are squares. This has all of its points converging to one point, 1, 2, 3, and 4. And then we get a rectangle reduced to a triangle with the base as a square. Thus, a square pyramid is obtained from a square prism by each of its points of one of the non-lateral face converging to one point. So one of the face exists, non-lateral face exists, but the other non-lateral face converges to a point, single point. Thus, a triangle is obtained from a rectangle. Is how I understand this as a very important note, where if one of its non-lateral face converges to a unique point, then I get a pyramid out of a prism. This is how I understand the transformation from a prism to a pyramid. Now this is one of the most important relation in mathematics or in this topic, which is called Eulers Relation. This relation is dedicated to Leonhard Euler, or we most probably pronounce him as Euler. So Euler's relation or Euler's equation is given for any polyhedra, as we already discussed in the previous session about a polyhedra. So for any polyhedra, the relation says that f plus v is always equal to e plus 2, where f is the number of faces and v the number of vertices and e the number of edges, which we already discussed for a solid figure, which is a polyhedra. So under these three different definitions, the relation is that fv and e are related with f plus v is always equal to e plus 2. Or this can also be taken as, when I add the faces and vertices and subtract from edges, I always get 2 as the value for any polyhedra which is considered in its case. So let's see how each of the cases happen. Say for example, I take a cube. So in this case, I know that totally the number of faces here, as I come with the case, is that there are 6 faces. 1, 2, 3, 4. 4 of the lateral faces and 1 on the top and 1 on the bottom. So there are totally 6 faces. Therefore my f, which is number of faces, is equal to 6. Then if I count with the number of vertices, I can see that 4 on the top and 4 on the bottom. Therefore 1, 2, 3, 4 on the top, and then 1, 2, 3, 4 on the bottom. So 4 plus 4, I have totally 8 vertices. Because v is the number of vertices, I have v equal to 8. Similarly, if I count the number of edges for this cube, I find that there are totally 1, 2, 3, 4, 4 on the top, 4 on the bottom, and 4 on the lateral. So 4 plus 4 plus 4, which gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my number of edges is 12. So that when I substitute these values in Euler's equation, my f plus v minus e would give me f 6 plus 8 minus 12, that is 14 minus 12, which is 2, and very much Euler's relation satisfies for a polyhedra, a cube. So let's take another example where I would like to apply a Euler's equation. Now this is clearly a polyhedra. So in case of this polyhedra, I clearly identify that there are totally 1, 2, 3, 4, 5. There are 5 faces, as can be clearly imagined. You can visualize this 3-dimensional object in imagination. I have 5 faces, 3 lateral and 2 non-lateral. So 3 plus 2 is 5. So 3 lateral and 2 non-lateral make a total of 5 faces for this particular solid. Now, if I count with number of vertices, I have 3 on the top and 3 on the right and 3 on the left. So this end gives me 3 vertices and the other end vertices give 1, 2, 3, 4, 5, 6. So that 3 plus 3 would give me totally 6 vertices. And when I count with the number of edges, I clearly count the number of lines I drew on the board, where 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have totally 9 of them, which are the total number of edges I count in case of this diagram. So when I apply this 3 in the Euler's relation or Euler's relation, then I get f plus v minus e to be 5 plus 6 minus 9, which gives me 11 minus 9 equal to, again, it is always 2 for any polyhedra taken into consideration would give me the Eulers relation to be true. This holds the relation between FV and V says that when you sum up the faces and vertices and remove the edges, then the value I obtain in case of any polyhedra is always 2, is what I understand for Eulers relation, dedicated to Leonhard Euler. So all the various polyhedras which we have discussed in this session of can be applied for Euler's relation. So any solid which forms a polyhedra can be identified for its number of faces, number of vertices and number of edges, and then add up these faces and vertices and subtract the edges, and we always get the value 2 in case of a polyhedra dedicated to Euler's relation.